Okay, so in three-dimensional area, we'll proceed on limit, continuity, and differentiability. Okay, so we are continuing discussion on limit, continuity, and differentiability. So what we have seen till now, that if a function or if a graph or if a kind of solid, if okay, so if there is a kind of solid material, and if how it can be uh, okay, if it is a continuous in a region. Okay, so there is a domain or there is a region. So this is a region. So if it is continuous in a region, if it is limitable, it is continuous, and then we can think about differentiability. So later we saw that not only limit is required, not only continuity is required, partial derivative is also required. So if continuity and both partial derivative along x-axis and y-axis, if both exist, then we can think about calculating the differentiability. So at any point in this region, any point AB, okay, if all the points in this region, okay, if this is a region, this is a domain, okay, so in this region, in this domain, if at every point, if it is differentiable, then I can say that over the graph is differentiable over the region. Okay, if it is continuous at all the point, then I can say that graph is continuous over all the domain or in a domain or over all the region R. If it is a kind of a limitable continuity, or we can calculate for a particular point a comma b. Okay, so if I am able to prove that this graph is continue for all the area, all the region in the in this all the in the domain in this region, then it is continue for the complete region. So that is the concept. So later we saw that if I am calculating at a particular point a comma b, then we have to calculate the continuity at a comma b. If it is continuous at a comma b, then we calculate the partial derivative along x-axis and then along y-axis, dz by dx, dz by dy, and then we calculate the tangential surface. So tangential surface at any point, like if I have if I have this 3D, okay, even though it is a glass, I believe it is visible in the camera. So if this is a 3D and I'm thinking about this point, and I'm trying to calculate the tangential surface at this point, it is as good if I go near to it, and finally I should start seeing it as a kind of a surface. Like I give example that if I look moon from here, then it look like a sphere. But if someone go near to it, then finally the moon, the point, what we see as a point on a surface, slowly that point someone starts seeing as a point on a plane. So that is the local linearity. Means local, if we go local, it becomes linear. Local linearity or tangential surface. So tangential surface to exist, I need to calculate both partial derivatives. What is the rate of change along x-axis? What is rate of change along y-axis? If I know these two, then what is the graph value at point A comma B? That is FAB. So FAB plus dz by dx, rate of change along x-axis, x minus a plus dz by dy, x y minus b, where z is function over xy. So z equal to fxy. So dfx by dx is a partial derivative along x-axis. Dfx by dy is partial derivative along y-axis. Now, if I have tangential surface, if I have graph equation, like there is a point called a comma b that is visible here as a black blue dot, okay, and there is a point on this sphere, then clearly we see that where this 3D meets this point, at that point, if this is tangential surface, this is lxy, and so that point both have same z value, but beyond that it is going in this direction, okay, we can see, and tangential surface is going in this direction. So tangential surface is going in this direction, whereas this sphere, this model is going in this direction. So everywhere, so if I keep it, then if it meets somewhere in the tangential surface, then beyond that there is a gap. Okay, at this point they are same, but beyond that there is a gap. So that gap is nothing but error. If that error is 0 at a comma b, then it has some value beyond that. So we calculate the limitation in the sense that at any point x comma y, if x and y is near to a comma b, if x y tends to a comma b, limit to a comma b, then the error what we are seeing, it should tend to 0. If it is happening, then it is differentiable. Means first that if we are calculating differentiation at point, if this is xy plane, this is not tangential surface now, this is xy plane. In the xy plane at any point a comma b, if we are calculating the differentiability, then if it is continue at that point, continuity exists at that point, and beyond that both partial derivative exist, then at this point, if this is the, now suppose this is the way I am moving the hand, so this is xy plane. If this is xy plane and this point is a comma b, at this point what is tangential surface, and at this point what is the sphere model. So tangential and sphere, they meet at a comma b, beyond that there is error. So if continuity exists and partial derivative exists, then we draw a tangential surface based upon the partial derivative. Okay, so we draw tangential surface based upon the partial derivative, and one tangential surface is drawn, and we know the fxy. So tangential surface is called lxy. So fxy minus lxy is the error. But when we are calculating in terms of differentiability, so what is differentiability? If I say that at point, if it is a 2D, means single line, at point A, if there is a independent variable x and dependent variable is fx, what is dfx by dx? So that is dfx plus delta x minus fx by delta x. Or if it is at point A, then it is dfa plus delta x minus fa plus delta x minus fa divided by delta x. If I consider 3D where I have 2 points a comma b, so if I am saying what is dfx by dx, dfx by dx, dfxy by dx, then then fa plus delta x comma b plus delta y minus fab divided by delta x square plus delta y square, because that is the distance that it has covered. So this is unit rate of change, means whatever the fxy has changed over 2 point, and the distance between 2 points is delta x square plus delta y square. So if that is the distance, earlier in line equation delta x is the distance. If someone has varies delta x in the independent component, then dependent component how much it has varied. If I know how much it had varied, then dependent component by independent component, the rate of change in the dependent component. Here also fa plus delta x b plus delta y minus fab divided by how much we took the independent component variation. So that is delta x square plus delta y square. Now same for the calculation of the error. if I am calculating error at error a plus delta x, b plus delta y, where a, b are point and delta x, delta y is an infinitesimal small distance in x direction, y direction from the a comma b. That will come as f a plus delta x, b plus delta y minus L a plus delta x, b plus delta y divided by delta x square by delta y square square. This is differential error or relative error we call it. Now, if I address x, delta x and delta rather than always saying delta x, delta y, I can say hk. So, f a plus h b plus k equal to error a plus h b plus k equal to f a plus h b plus k minus L a plus h b plus k divided by h square plus k square square. So if this relative error, when we are limiting h and k to 0, if this relative error becomes 0, means where the tangential surface touches the graph, at that point, it is error is 0 because the both are at same z value, fx value. So when we limit h and k to 0, then error a plus h b plus k also should become 0. When h and k tends to 0, then a plus h, error at a plus h, b plus k should be equal to error at a comma b. That is 0. Okay. So, or at any xy on this plane, any xy, if xy tends to a comma b, then error at xy, where xy tends to a comma b, should be 0. So this is the one way that we calculated the differentiability, making it to 0, and we see that it satisfies this condition or not. If it satisfies, then it is differentiable at point a comma b. Now we came with even ahead that if I know in a region, if I know that if I calculate the partial derivative, okay, I calculate the partial derivative, okay, this is x direction, this is y direction, this is xy plane. So dz by dx means how much is the slope along x-axis. dz by dy, how much is the slope along y-axis. So if it is like this, then it has slope along x-axis and y-axis. If it is like this, then there is no slope along x-axis, but there is slope along y-axis. If it is like this, then there is no slope along x-axis and y-axis. If it is like this, then there is slope only along x-axis, there is no slope along y-axis. So, slope is nothing but dz by dx and dz by dy along x-axis and y-axis. So, that is the scenario. Now, if I have calculated slope along x-axis dz by dx, and this comes as a function of xy, not required always. Sometimes it comes as constant also, sometimes it won't come. Then we say that partial derivative do not exist. But if it comes in the equation of x and y, dz by dx, dz by dy, when it comes in function of x and y, and if we see x and y, the whatever we get dz by dx is a function, is the equation. dz by dx, dz by dy both are equation in terms of x and y, in function of x and y, and they are continuous over a region, then it is said that in x direction it is continuous, it is differentiable and continuous, means full differentiable. I mean, in full area it is differentiable. In y direction, full area it is differentiable. If that is the case, then it is partial derivative exists and it is continuous along x-axis. If partial derivative exists and it is continuous along y-axis, then it is differentiable along the on the full region. So no need to calculate limit, continuity, anything. Just do partial derivative. And if it comes as a function and both partial derivative dz by dx and dz by dy, they are continuous along x-axis and y-axis, then full region is differentiable. If it is differentiable along x-axis and full continuous, differentiable of y-axis and full continuous, then it is differentiable along x-axis. It is differentiable in the particular region. So if this is so in calculus, if this is a xy plane, then all points here are xy, and whatever we say fxy, that is the vertical direction. That is the value against that point. If I say this is xy, this is x and y, then if I compute fxy, if this is a Python function is f, and if I push xy as a parameter or call it through argument or push as a parameter to the function, whatever it returns, that is the vertical value. Okay, so that is function over x and y. That is the scenario in the 3D. Okay, now we saw the case that if it is continuous and if it is both partial derivative, then we can think about differentiability. But in other way, if it is partial derivative and continuous, then certainly it is differentiable. What we see, right? If it partial derivative and it is continuous in both directions, then certainly it is differentiable, but not required that if it differentiable, then it is their partial derivative are continuous. So continuous and partial derivatives are continuous. That is more strict case, most stringent case. On that side, if it is continuity exists and both partial derivative exist, then only you can think about differentiability, but not require that differentiability would happen. But if it is differentiable, then it is guaranteed that it is continuity exists and both partial derivative exist. On this side, if partial derivative are continuous, guaranteed that it is differentiable over the region. But if it is differentiable, then it is not required that both partial derivative are continuous. Both partial derivative would exist, but their continuous over the region is not guaranteed. Okay, so you can prove it. Means there are something that you can also do. So you can prove it. Now we give the example of cone. So if I have a cone, so if I have a okay, so if I have a cone that is fxy equal to x square plus y square root, then we saw it is continuous at if this is a cone and this is 0 comma 0, then it is continuous at 0 comma 0, but partial derivative do not exist, so it is not differentiable. One case we saw. Another case is fxy equal to xy by x square plus y square. It is not continuous at 0, 0. So fxy equal to xy divided by x square plus y square. It is 0, it is 0 when xy is 0, 0. It is not 0 when xy is not 0, 0. If that is the case, then it is not continuous at 0, comma 0, whereas partial derivative exists. But differentiability needs both of them, so differentiability does not exist. Now we'll see a case where partial derivatives are possible and partial derivatives are possible and continuity does exist, but it is not differentiable. Differentiable need continuity and partial derivative to exist, but not guaranteed that differentiability will exist. But if it exists, then continuity and partial derivative would exist, that is guaranteed, but not the other way. Now consider that fxy equal to x to the power 1 by 3 and y to the power 1 by 3. Fxy equal to x to the power 1 by 3 into y to the power 1 by 3. So certainly it will be 0 when xy is 0, not 0 when xy not 0. Now we'll first calculate the partial derivative. So partial derivative will be, first it will be if dz by dx if I do, first it will be in both dz by dx and dz by dy, both will be in terms of x and y. So I would not go further. So x to the power 1 by 3, y to the power 1 by 3, if I derive it, if I do the derivative where y is constant, then it will come as 1 by 3 x to the power minus 2 by 3, y to the power 1 by 3. So function fxy equal to x to the power 1 by 3 y to the power 1 by 3. So it will come as 1 by 3 x to the power minus 2 by 3 y to the power 1 by 3. Same it will come as dz by dy. 1 by 3 y to the power minus 2 by 3 x to the power 1 by 3. Okay, but if x and y at point a comma b, where a comma b is 0 0, then both partial derivative will come as 0. If both partial derivative exist, 0 means it exists, so partial derivative exists. So now tangential surface at a comma b, LA plus HB plus K is FAB plus M, that is dz by dx x minus a dz by dy y minus b. So their partial derivative would be 0, FAB is 0 and 0, 0. So tangential surface is 0. Means tangential surface for the equation x to the power 1 by 3, y to the power 1 by 3 is 0. Means it is, there is no variation along x-axis, there is no variation along y-axis, so it is horizontal to the ground. So the tangential surface or local linearity. So if x to the power 1 by 3 and y to the power 1 by 3 is this, then if it touches 0 comma 0, okay, then the tangential surface is horizontal, because there is no variation rate of change along x-axis, there is no rate of change along y-axis. Now let's calculate the continuity. So it is continuous or not. So x to the power 1 by 3, y to the power 1 by 3. So that is the idea. For continuity at a plus h, b plus k, we will replace it by a plus h and b plus k. So a plus h to the power 1 by 3, b plus k to the power 1 by 3. Now a and b are 0, 0, so h to the power 1 by 3, k to the power 1 by 3. Let's consider that h and k are same. What is h and k are same? Okay, so calculus is a science where it cannot afford bypassing anything. Each and every point should be crystal clear. What is h and k? Now suppose that this is point a comma b. This is point a comma b in this region. Okay, this is point a comma b, and h is, or delta x is, a small displacement along x-axis. Delta y or b, delta y or k is a small displacement along y-axis. So suppose this is the point h and k. This is the point h and k. This is the point h and k. This is the, anywhere h and k could exist, depend upon the value of h and k. If h and k is here, then k is 0. If h and k is here, then h is 0. Now if I take h and k same, then certainly they exist along the 45 degree. Okay, they exist along the 45 degree, or they exist along this 45 degree, both are negative. Okay, if they are same, then now a plus h to the power 1 by 3 and b plus k to the power 1 by 3, a and b are 0. At 0, 0 we are trying to find the continuity. Then h to the power 1 by 3, k to the power 1 by 3. If both are equal, then h to the power 2 by 3. If h to the power 2 by 3, then it is continuous, because now the continuity is directly proportional to h. Now, if I calculating a comma b and h is at a small distance, okay, so if h is at a small distance here, then the way h is growing, the continuity is growing. This is what is expected. Either it should not be constant. If it is constant, then it should not be discontinuous, like uh, like absolute value plus minus 1 plus minus 2. So in x direction it is 1, in y direction minus 1. So it will go like this, come like this, so it is not continuous. But if it is it is in variation of h, when h is 0, then there it is 0. This is what is required. The function is 0 when xy is 0, a b is 0, x to the power 1 by 3, y to the power 1 by 3. So if continuity is h to the power 2 by 3, directly proportional, when h is 0, it is 0. This is what is required. But the way h is growing infinitesimal distance from a comma b, then it is infinitesimal big. So the way h is growing, this is also growing. So looks like this is continuous. So it is partial derivative exists and it is continuous also. So nice. Now we can think about the differentiability much away. Now for calculating the differentiability, that now if we have this is tangential surface, this is xy plane somewhere, and this is tangential surface. Here tangential surface is parallel to xy plane, and here the x to the power 1 by 3, y to the power 1 by, suppose this is the model, it touches the, okay, the plane, tangential plane, where the xy is a comma b, that is 0 and 0. So error at a comma b is 0. That is what we are saying, okay, because the error is nothing but the gap. If I consider this and it is touching here, that is 0 0, then this is the error. So here there is no error and error is growing. So when error is not available at a comma b, then error at a comma b is 0. So if I am trying to find error at any distance h and k along x-axis and y-axis, then a plus h and b plus k, at that point error should be 0 if h and k tends to 0 0. Okay, this is limiting. So if I limit h and k to 0 0, then error should also be equal to 0. That is that 0 error at FAB. Now error at a plus h and b plus k is f. The error at any point is whatever the graph equation is and whatever the tangent. If I subtract this, that is the error we are getting. So f a plus h b plus k minus l a plus h b plus k divided by h square plus k square square root. This is how we are calculating the error. Now if now f a plus a and b we are taking at 0. So f h k minus l h k divided by h square plus k square square root. This is the error. Now we are limiting h and k to 0 0. It's all right. Now FHK is h to the power 1 by 3, k to the power 1 by 3 minus LXY or LHK is FAB plus m dz by dx x minus a dz by dy y minus b. So dz by dx, dz by dy, FAB all are 0. So it will come as FHK, that is h square h to the power 1 by 3 k to the power 1 by 3 divided by h square plus k square square root. So if function fxy is equal to x to the power 1 by 3, y to the power 1 by 3, then the error at a plus h b plus k is fhk minus lxy is 0, fhk divided by h square plus k square square root. Then it will come as h to the power 3, k to the power 3 divided by h square plus k square square root. Now consider that h, k are same. Then h to the power 2 by 3 divided by 2 square, okay, 2h square square root. That will come as the square root of 2h. So h to the power 2 by 3 divided by a square root of 2h, that will come as 1 by a square root into 1 by h to the power 1 by 3. So the error is inversely proportional to h, or error is directly proportional to 1 by a square root into 1 by h to the power 1 by 3, or error is inversely proportional to the growth of h, because it is inversely proportional to h to the power 1 by 3, or it is proportional to 1 by h to the power 1 by 3. So 1 by square root into 1 by h to the power 1 by 3. So if h is coming near to 0, then error grows. If h is going far, then error reduces. Whereas if h is going far, then error should increase. If h is coming near to origin or a comma b, error should decrease, and typically it should become 0. But that is not the case. When h and k when h and k are coming to near 0, when h is coming near to 0, since it is 1 by h to the power 1 by 3, so the error is becoming growing, and it is becoming infinite when it is infinitesimally small distance from the origin. So no use. It is not differential. It is partial derivative exists 0, 0. It is continuous, both are because that is directly proportional to h, but it is not differential. So, if I draw the graph of x to the power 1 by 3, y to the power 1 by 3, then the point at 0, 0, it is not differential. Even though partial derivative along x-axis, partial derivative along y-axis, okay, they exist at point 0, 0. It is continuous also, but it is not differential. So differentiability requires continuity and both partial derivative to exist, but not guaranteed that it will be differential. Okay, that is the big thing. Now we'll go to kind of if it is not enough. Okay, so we'll go to the kind of a final, that is, if partial derivative are continuous, then it is guaranteed that it is differential. Okay, if I consider this scenario, because theoretically we have seen that. Now suppose fxy equal to log x to the power x square plus y square. Fxy equal to ln natural log in bracket x square plus y square. If that is the case, we'll calculate the dz by dx. So dz by dx would come 2x by x square